Hey team, we are about to dive into studying the fundamental reactions that power living systems here on Earth, photosynthesis and cellular respiration. And in order to understand these reactions, it's important to know a little bit about the ways in which cells store and metabolize energy, and why we store energy in the different forms that we do. So this is just a brief kind of reintroduction to some organic compounds that you already know and love, and then an introduction to a new topic called chemiosmosis. Okay, so there are four major ways in which cells store energy, and they all have slightly different benefits and drawbacks. So lipids and fats and lipids. So you know this image below is a triglyceride. It's composed of 3 fatty acid tails and a glycerol head. It's a really calorically dense molecule. It means there's a lot of energy contained within the bonds that hold this organic compound together. There are actually 9 calories per gram in fat. It's also very hydrophobic, so as a result, it doesn't like to bind with water, and the result of that is that it doesn't absorb really any water, and therefore it's a relatively light form of energy. It's not very heavy. Fat is a really efficient way to store energy for long-term use, but it's not super accessible, and it has to be changed into a different form in order to use it in cellular processes. So lipids are kind of like your savings account. It's there, you can access it, but you don't want to be dipping into your savings account every day, because that's not, good for your long-term financial planning. Carbohydrates, I guess a little bit in contrast. So carbohydrates are very hydrophilic, therefore they absorb a lot of water. This is an example of glucose, and when glucose takes the form of glycogen, which is how you store glucose in your body, every gram of glycogen absorbs 2 grams of water. So it ends up being a really heavy way to store energy. However, it's a little bit easier to move glucose around your body than it is to move fat around your body because it is hydrophilic. It means it can dissolve into aqueous solutions, which your cells are in, and then it can be easily transported through the bloodstream from one cell to another. So part of the benefit of this form of energy is that it's a lot easier to move around than it is to move around fat. So it's a little bit less calorically dense. There are 4 calories per gram of energy in glucose, but it's a little bit easier to convert it to usable cellular energy than it is fat. So say carbs are like our checking account. They're moving in and out of the body, and more easily moved around than fats are. But it's still a little bit harder to access these funds than it is to use ATP, which is like cash in your pocket. So ATP is the molecule that is just the right size to do cellular work. It stores smaller quantities of energy than glucose or fat, but it's just the right dosage in order to make things happen in your cells. It stands for adenosine triphosphate. Adenosine is just the nitrogen base A, and triphosphate means that there are 3 inorganic phosphate groups linked to it. When it goes through a hydrolysis reaction with water, this bond between the two most distant phosphates are broken, and energy is released in that process. And we can use that energy to do a bunch of different types of cellular work. For example, we can use ATP here to take two different organic compounds and then fuse them together. We can take ATP and use it to pump solutes, dissolved things in aqueous solution in the cytoplasm of cells. We can use it to pump these things across a membrane against their concentration gradient. So remember, this is active transport. We're moving things from an area of low concentration to an area of high concentration, so it takes work, and we can use ATP to do that work. And then we can also use it to do mechanical work. This is an example of a myosin and actin, which are the two filaments that are in your muscle cells, and we can, using ATP, we can actually move them relative to one another. This is a little motor protein, and when ATP is broken off of this motor protein, it pulls this way on the actin, and it causes a muscle contraction. Okay, so ATP can be used for all these different types of cellular work, and it's just the right balance of good for storing energy, but it's easy to release that energy. Whereas with lipids and carbs, it's a little bit harder to release that energy, and there's more energy stored in them. Okay, the last form of cellular energy, the ways cells can store energy, is through chemiosmosis. And chemiosmosis is the movement of ions across a semi-permeable sorry, it's too early, I can't spell. Across a semi-permeable membrane down their electrochemical gradient. Okay, before we dissect what this definition means, I want to give you the analogy of between chemiosmosis and a hydroelectric dam. So, as many of you are probably aware, down in Wilder, we have a dam blocking the flow of the Connecticut River. The way that a dam works is that it's placed in a river where there's a natural concentration gradient. We have an area of high potential energy, and relative to an area of lower potential energy downstream. So rivers are always flowing from higher altitudes to lower altitudes. So you have high potential energy, and then you have low potential energy. But energy is always conserved. So this means that the energy cannot be created or destroyed. It just is converted from one form to another. So if you have an area of high potential energy, this means as it moves to an area of low potential energy, you're going to have an area of high kinetic energy. So that means that this water is flowing fast down here. Okay, so a dam blocks the flow of the river, and you build up an area of high potential energy above the dam relative to this area of low potential energy and high kinetic energy downstream of the dam. And then some water is selectively allowed to pass through a channel in the dam, and it spins a turbine. When this turbine spins, it actually moves a magnet relative to a coil of wires and in a generator. So this is a generator. There's a relationship between electricity and magnetism, and not going to get into that here, but if you're interested, you should come talk to me later. But the end result is that we have we create a current, and we use that to power our homes. This creates electricity. But the main point that I want to get across here is that we use this concentration gradient in order to do work and transform energy from one form to another. So we start out with potential energy of water based on its location in the dam, and we end up with lights turning on in our homes. So we can use this gradient in order to do other forms of work. Okay, chemiosmosis is using this same concept, but instead of a hydroelectric dam, our dam is a cell membrane. And instead of water on one side or the other, the concentration gradient is ions. In this case, it's hydrogen ions, H+. A hydrogen ion, remember hydrogen is the first element in the periodic table, and a hydrogen ion is actually just a single proton. So this side of the membrane is an area of high concentration of hydrogen, and relative to the other side, which is a lower concentration of hydrogen ions. And so as a result, there is a gradient across this membrane. But remember, because the membrane has a hydrophobic interior, it doesn't want to interact with these ions, which are all charged. They're all just one single positive charge, and they can't move through the membrane directly. We call it both a chemical and an electric gradient because all of these protons have a positive charge on it. So if we look at, there's a chemical gradient because there's more hydrogen on this side relative to this side, but it's also electric gradient because there's more positive charge on this side relative to this side. Okay, so we can use this gradient in order to do cellular work or create the type of cellular energy that we need by passing or allowing these ions to diffuse down their concentration gradient through a special membrane protein called ATP synthase. So ATP synthase, when hydrogen ions push through it, because remember, there's a push here because there's more hydrogen on this side relative to this side. There's a push through this molecule. This membrane protein actually spins in the membrane. So it rotates as these hydrogen ions move through. And we use that kinetic energy of the spinning of this protein to drive a chemical reaction, which is taking ADP, which is adenosine diphosphate, adenosine with two phosphates on it, so basically this molecule right here, and with free phosphate in the cell, we bind the two together to form ATP, adenosine triphosphate. So it's basically this reaction running in the opposite direction. Instead of releasing energy, we are consuming the energy of this electrical chemical gradient in order to make more ATP. So this is chemiosmosis, and you're going to see this process in both photosynthesis, which is the first reaction that we're going to study, and cellular respiration. So it's another way that cells store energy and use it to transform energy from one form to another. Okay, that's all.